Welcome to another episode of Statomatic Science. Today we're looking at the turntable again, and I think we're going to do some real work on it this time. If you're new to this channel, this project encompasses my goal of building a fully automatic turntable that I can use to play my records on, but I also want this to be built out of commonly found parts so that anyone can find the parts and build one if they want to. In the previous episodes, we found closure with the past of this project, looking at my two original prototypes, which had some problems, but I'm coming back to this with a fresh pair of eyes, so I think I have ideas of how to solve these. Today I'd like to go over the basics of the project, the lift mechanism, and to get started with the code. So let's get to work. Like with every project, instead of mindlessly throwing things together, because I know how that ends when I try it, I'm going to start with a plan. And this plan isn't going to go into implementation specifics, but more so cover the overall goal. Implementation specifics, well, we'll talk about those in more detail as we go. I put together this diagram to show what my goal is for the project, which will hopefully become the first model of my automatic turntable. Though I want the automatic functionality to be fully capable, I limited the main features on the user interface to just things that I would find useful on a turntable. So we have an 11.5-inch platter, meaning a 12-inch record will hang about a 1/4 inch off the edge. And this makes it easy to pick up a record from the turntable, both for a human and for the automatic mechanism that I plan to build for this in the future. The tonearm is tonearm length. Not a whole lot to say about that, but I'll figure that out later. It'll have a rest and a lift mechanism. That's not on the diagram, but you'll see those later. Over at the controls, I'm planning to let the user pick 12-inch, 10-inch, or 7-inch sizes, if they know what size they want, or let the turntable automatically determine the size. The squares over here will be LEDs illuminating the setting that the user has selected, while this circle is the button that will cycle through the settings. Down here, we have a similar story with the turntable speed selection. The user can pick 33 1/3, 45, or 78 RPM, or attempt to automatically determine the speed. I'm planning to use the automatic speed determination based on what speed's most common with each record size. So for example, a 12-inch record would be 33 1/3 RPM, a 7-inch record would be 45 RPM, and a 10-inch record would be 78 RPM. I'd also like to point out that there is no strobe or speed readout on this diagram because I didn't plan to include those. The speed will be digitally monitored internally, and I have no desire for fine-tuning controls on this user interface. So we're just going to keep it simple and allow selection of the most common values. Lastly, we have some basic commands: a power button, play button, and pause buttons. Those are going to work exactly how they worked on the previous prototype. Overall, my goal here is to keep the user interface as simple as possible. There's a million different features I could put on here, but I want to include only the ones that I know that I'm going to use. On the back of the turntable, we have some other stuff going on. Starting with some basics, we have the left and right audio output and ground. I'm not planning to give this a built-in preamp, but I might build an add-on on the back that functions as a preamp. On the other side, there is quite a bit more going on. We have our 120 volt input, a USB connector that'll allow me to plug this into a computer so I can easily write firmware to it, a calibration button that'll be used to calibrate the automatic functions, and a reset button that will reset all the user settings to their default values. The reset button might not be necessary, but it's an easy addition, so I figured I might as well include it. Up here we have my personal favorite part of this project, 5 serial communication ports that you'll be able to connect up to 5 add-ons concurrently. I have tons of ideas for what these add-ons could be, but ultimately these will allow the user to unleash every single possible feature this turntable has to offer. Some of these modules could be a record flipper, a record changer, a second tonearm, an FM transmitter, a preamp, an alarm clock, a full-fledged feature-rich control panel, a remote control receiver, and so on. There really are so many possibilities here, and that's why I'm keeping the included features to a bare minimum so that I can make this essentially modular. And I've had this idea of modularity since the beginning with this project, and I formally achieved this using logic gates, which work fine for connecting one module. But with this version, I want to handle all external commands via serial, which will allow me to connect multiple devices concurrently, and make it so that I'm not tied to specific hardware to execute certain commands like I was before. If I want to add a really specific command for a module, I could easily do that in the software without making any hardware changes. Now, why am I doing 5 serial ports instead of 1 or 2? Because I could. I don't know. I want to. So that's it really. If we stick to this user interface and these features, I think we'll be set for this project. In terms of digital control, I'm planning to use the Teensy 4.1 microcontroller. This has more than enough pins to accommodate all these features and is one of the reasons why I felt comfortable dedicating so many of them to serial communication. Here's a really rough schematic of what I'm thinking our pin usage will look like. If you have a keen eye, you might have noticed that I'm still doing a lot of multiplexing, even though in the first episode I said I would just get a microcontroller with more pins. Well, I have more pins now, but I still need to multiplex, so what changed? In the previous version, a lot of the turntable's state was maintained on the hardware. Physical switches would be set, which would alter the state. Similarly, for the back control panel, the state would be manipulated, setting certain pins high or low. Because of this, you could tell what settings the turntable currently had because you just look at the switch. In this version, however, I want the entirety of the turntable's state to be maintained digitally. Not only does this reduce hardware cost, but this also makes it easier to make changes in the future and allow external modules to alter the state as needed. Because of this, we need status LEDs, so the user can see what setting is currently active, and that's what fills up most of this 16-bit shift register. This allows me to take all of these output values and consolidate them to 2 microcontroller pins. None of these statuses are time sensitive, so that makes them perfect to live here. Similarly, I have all the user interface buttons on this multiplexer, which only takes up 4 pins total. None of these are time sensitive either. Next, I'm probably going to multiplex the vertical and horizontal stepper motors, just like before. These motors will never need to be running at the same time, so this made sense to save 3 pins. With all of that optimization, we have 4 empty pins remaining on the microcontroller. Now, if I don't have to add anything to this design, I should be able to eliminate the vertical and horizontal muxes. But I suspect something unexpected is going to come up, so I'm going to leave them open for now. The rest of the pins just accommodate everything I think we're going to need for the turntable. I'm not going to go into a ton of detail with what all these things are doing right now, but we will touch on each one as it becomes relevant. Now that we have our homework out of the way, let's look at the main parts that we need to make this turntable functional. And the way I see it, we need vertical movement, horizontal movement, and a turntable. That's basically it. Now, I ordered those things not only by their predicted difficulty, but in the order I'm going to accomplish them. I know they're all possible to do, I just need to figure out how to do them. So I'm going to warm myself up with probably the easiest one, which is the vertical movement, and that's the lift assembly. In the first version, I used a crude rack and pinion type setup where the lift mechanism would bump into an upper or lower limit switch. Later on, the rack and pinion became O-rings and friction, which worked a little more smoothly. This setup did work fine, but it was insanely inconvenient to calibrate it. You basically had to have it completely apart if you wanted to make any adjustments to how high the tonearm lifted up. Also, you could never adjust the lift's range. It was perpetually determined by the spacing of the limit switches. In this new version, I would like to solve both of those problems, and what I've chosen to do to accomplish this is to use a slide potentiometer to track the position of the lift. And this way, we just have to set our upper and lower limit on the potentiometer, and then we can set that in software, and theoretically, this could be calibrated automatically. To drive this movement, I'm planning to use the same stepper motor as before, but instead of using a rack and pinion for friction, I'll use a string being tensioned to drive the lift up and down. But if this doesn't work, I don't know, I'll figure it out. I'd like to get away with using the same parts for different things as much as possible, so there might be some inefficient ways I'm doing this that I technically could get something a little bit better to accomplish what I'm trying to accomplish. But if I can reuse the same part for multiple things, that makes it a lot easier to buy parts in bulk, and it makes the project overall cheaper. So we have our plan. Let's build it. The first thing I did was make something to couple the vertical shaft movement with the potentiometer. I'm going to try to get away with only using one bushing in this design, mostly to save on vertical space. I was a little concerned at first, but it seems like everything moves smoothly with one bushing. So I think we're in the clear for now. Next, I designed the cap that would house our pulley, and I used fishing line to pull. So far, this design seems promising, though in this iteration, the shaft doesn't automatically lower itself. After that seemed like it would work, I hooked up a stepper motor to the pulley. Initially, I was a little concerned the motor wouldn't have enough torque to drive the mechanism, but man, I was so wrong. I forgot how much torque these little 5-volt steppers have. Their internal gears are more than pulling their weight here. In fact, this motor had so much torque that it bent the 3D printed frame if it kept stepping at the upper limit. I experimented a bit with how much weight this thing could lift, and I never found its limit, but it was lifting a solid 13.4 ounces or 380 grams, so way more than enough to lift a tonearm. My next goal was to figure out the minimum amount of weight needed to lower the mechanism to its lower limit so I wouldn't have to push it down, and I did this using a bottle of water, just emptying it until I got it to what seemed like a good point. I determined this was around 8 ounces or 227 grams, so my next task was to find a spring that would appropriately supply this force downward. This was a harder task than I thought, as there were not a lot of spring options that fit the very specific specifications I was looking for, but I guess that makes sense since it's November as I'm recording this, so they're out of season. But I did find one, and with my tunnel vision at its peak, I bought a few of them. And while I waited, I refined this design a little bit until I had it a bit more reliable. For the pulley's axle, I used a cut-up paperclip. I never realized just how useful these are for projects like this. I made my Arduino code spit out the potentiometer's values as it moved, and yeah, that's definitely working. I also wired up the lift sensor itself so I could detect when it's grounded. Another thing I wanted to do while I waited for my springs was come up with a backup plan. The more I looked at this design, the more I doubted it, so I wanted something to fall back on in case it didn't work. So this is the next thing I tried. I attached an idler to the stepper and added some springs to pull the lift coupler into the idler. It could move in both directions, but it slipped a lot, so it seemed even less reliable than the previous version would probably be. My next attempt involved making the stepper's rotary movement push the lift up and down. Not too dissimilar to couplings servo motors typically have. This mechanism was super simple, but it worked perfectly. But the lift wobbled way too much. I don't need this thing to be perfect, but this just looked terrible. So I gave in to the thing I kept trying to avoid, which was the lower bushing. Once I added this, things were looking much better, and the only thing I lost was a little bit of vertical space. Oh well, I'll make a hole in the bottom of the final assembly if I have to. I'm going to interject here. You probably heard the word servo earlier and wondered why am I not using one of those. They're cheap, easy to use, and they achieve exact positioning just like what I'm looking for, so what gives? With a stepper, I have much better control of the speed at low RPM, and with a servo, they're not modular, so if one part fails, I have to replace the whole thing. And this one's a little petty. I just don't like the sound they make. My previous turntable had a linear actuator that had little plastic gears that sounded like this, and I hated it, so I'm not going to do that with this one. Anyway, I took the assembly and mounted it to some scrap wood and scrapped together a mock tonearm so we can really visualize how this is going to work. The tonearm doesn't have a counterbalance weight yet, but it still lifts with ease, so I think this is going to be more than enough power to lift it. I have this LED hooked up to indicate when the tonearm is making contact with the lift. This is going to help with moving only the needed distance instead of two hard-coded points. Here I'm demonstrating how that's going to help us. You can see the LED turns off when the tonearm stops moving down. We can use that information to know if we've landed on the record, the home mount, or missed our mark entirely. I'm doing that by completing the circuit through the tonearm and the lift rod, which is coupled to a wire that's just kind of smashed in there. I'll make it nicer later, I promise. One problem you might have noticed is that when lowering, the mechanism appears to stop for a brief moment when disconnecting from the tonearm. And this is because there is quite a bit of play in the mechanism, like way too much play. Technically this will work fine, but it bothers me, so I'm going to try to fix it. I totally thought my 3D printed coupling would be mostly at fault here, but it turns out the motor itself is what introduces most of this play. I really didn't want to change motors, so I attempted to rectify this by making the 3D printed parts tolerances as tight as possible, and adding a spring to constantly pull the lift down. This way, the lift is always sitting at the bottom of the motor ply. I also cleaned up the wire coupling so that it could be a lot more reliable now, and I filed the paperclip piece and greased it using white lithium grease, which should keep everything in good condition. When I tried adding my spring, it didn't have enough tension to pull the mechanism down, which makes sense because the upper and lower bushings being even slightly out of alignment, combined with the slide potentiometer, created way too much resistance. So I took the spring off, said, it's good enough, it'll work, and then I put it back together. To my surprise, the problem that bothered me was gone. Turns out it was my 3D printed part that was the problem. Oh yeah, my springs got here eventually too, but I've already moved on from the design that required them, so we'll just use them for another project. Someday. So we have our mechanism complete. The next thing I wanted to do was implement the circuitry that would drive this mechanism as it will on the final version. What I started with was looking at my diagram from before and identifying the parts I'd need to accomplish this. It's looking like we'll need the input multiplexer and the movement motor multiplexer. Sounds simple enough. Let's flesh out those parts on the schematic. And here's what I ended up with. This might look a little daunting at first, but I promise it's a lot easier to understand if we break it down a bit. Our multiplexer, for which I chose the TI-CD4051BE, handles all the user input values, so play, pause, size, speed, and so on. These inputs are all pulled low with 10K resistors, and then we have connectors that the actual buttons will get plugged into. Now this is a multiplexer, so we can only acknowledge one of these pins at a time. We select which one we're acknowledging using these three select pins, which boil down to basic binary, with pin A being our least significant bit. Once you have your pin selected, pin 3 on the IC will give you the output of that pin, which I plan to read on pin 7 of the TNZ 4.1. Moving on from the input multiplexer, we get to my least favorite part of this whole design, which is the motor select circuit. The only reason I'm multiplexing these is to save 3 pins on the microcontroller, and if I get to the end of the project and have 3 free pins, I'm totally eliminating this multiplexing. Anyway, each mux represents 1 pin needed to control the stepper motor, so we have 4 of them and they all choose one of 2 outputs based on 1 microcontroller pin. So if I set this pin high, then all of the muxes will forward the microcontroller control to the horizontal motor. Low, and we control the vertical motor. And here's the lift circuit, which is going to be pulled up internally within the microcontroller, so we connect that to ground to toggle our lift status. So with this plan, we should be able to get our button input working, our lift movement working, and our lift sensor working, and having them all nicely talking together. Everything starts with user input, so I wrote a multiplexer library that monitors all user inputs without using any loops. All you have to do is call this monitor method every loop cycle, and then you call getValue to get the current value of one of your pins. And this value could be 1 of 6, with released being the default for a button. On press would be when you first press a button, press comes immediately after on press, which remains the status until the button is held long enough, in which case the on hold status will get set. One loop cycle later, an on hold will transition to the held status. When releasing the button in the on press or press state, it will transition to on release and then released the next loop cycle. When releasing a button in the held state, it will go straight into released because I don't want on hold and on release events to both be executed from one button press. Just one or the other. Okay, now that everything appears to work on paper, I got started with translating my schematic from earlier to the breadboard. This is a long and tedious process, so I put on Tornado by Yes and got to work. After some troubleshooting and realizing I missed a couple wires initially, everything seems to work perfectly. I can light all the buttons up by pressing them, and if I hold one of them for the whole duration, they shut off. Now, I know I had 10K resistors on the schematic, but I used 22K here. That's all I had on hand. Alright, cool. That's one part of the circuit down, so let's go see what the stepper circuit's got going for it. On the schematic, I'm using 4 multiplexers that have a really long name, so I'm just going to call them Jim. Jim is a surface mount component, which is great because that means he's small and cheap, but what isn't great is that my breadboard doesn't like this. Rather than buy a breakout board to give Jim his breadboard debut, I used the ADG333A multiplexer, which has the perfect form factor for the breadboard, and has 4 circuits, meaning I only need one of these. This part's obsolete, so it's a little bit pricier to get your hands on, so this chip will only be present for the prototype. Anyway, I started translating the motor control portion of my schematic to the breadboard, which turned out to be successful. Over here we have our multiplexer, which divides up our motor control into our motor driver. Also on this breadboard, I'm using brown wires to denote 3.3 volt lines and red to denote 5 volt lines. Okay, so I have my hardware connected to the microcontroller, so it's finally time to start writing real code. Here it is going all the way to the upper and lower limits when I press pause and unpause. Now, when I put something there for the Mach tonearm to set on, the lift doesn't go as far down. If I remove the thing it was setting on, the button will make it go down the rest of the way until it's at the lower limit. But I think this is wrong. It should probably go up in this scenario, so I modified the code to do that. Alright, this turned out way better than I expected it to. I was expecting it to work, but I was not expecting it to work this well. It's moving the exact same distance every single time below the tonearm. I'm not the greatest at 3D modeling, and it doesn't help that I'm using Google SketchUp 8 for all of these models. So everything you see designed here was designed in Google SketchUp 8. And you know how it goes. It's easy to make something work. It's difficult to make it work well. But despite that, I'm pretty happy with how everything came out so far. Also, I would like to mention that everything I worked on here, schematics, code, diagram, everything is completely open source. So if you want to take a look for yourself, feel free to click the GitHub link in the description. And with that out of the way, we still have a ton of work to do on this project, but I'm super happy with the progress we were able to make in this episode. In the next episode, I'd like to take a look into finalizing the tonearm assembly. This implementation you see here is kind of just a mock implementation to let me test the vertical movement, but I want something that's a little bit more standardized and looks a little bit nicer to test with the horizontal movement. Thank you so much for watching. I really appreciate all the support you guys have given in the last videos, and I'm looking forward to continuing this project and painting a clearer picture with every episode of what I want this turntable to look like. Alright, that's all I got for you today. I'll see you in the next one.